In this episode, we're taking a deep dive into one of the more notorious mysteries of the ancient world, the granite quarry of Aswan, located in Upper Egypt.
There is a 1,200-ton stone in Egypt that shouldn't exist. It sits in a granite quarry on the east bank of the Nile, 3 times heavier than anything ancient Egypt ever successfully moved, abandoned mid-extraction by the people who started carving it 3,500 years ago. Modern engineers still cannot explain how they plan to finish.
Quarries like this one are incredibly precious resources, in some ways even more important to deciphering the past than are finished monuments or artifacts.
The strangest part isn't that they failed. The strangest part is that they started at all. Why the Egyptians built monoliths. The stone is called the unfinished Obelisk. It lies in a quarry on the outskirts of modern Aswan, still partially fused to the bedrock on its underside, frozen in mid-extraction. It measures 137 feet long, taller than a 12-story building. It weighs 1,168 tons. To understand why that number is impossible, you have to understand what an obelisk actually was. An obelisk is a single piece of stone, carved into a tall 4-sided shaft, with a pyramid-shaped tip called a pyramidion. The shape was sacred to the sun, god Ra. The pointed peak caught the first rays of the rising sun, connecting the monument to the divine. Obelisks were not decoration. They were theology rendered in granite.
Going by the orthodox timelines, we know that the quarry was in use for at least some 1,500 years before this.
And by deliberate design, they had to be monoliths. One piece, base to tip, no seams, no joints. The unity of the stone represented the unity of the cosmos. A crack would break the symbol. This theological rule created an engineering nightmare. You had to find a granite outcrop large enough to contain the entire finished object. You had to separate it from the bedrock, using tools softer than the stone you were cutting. You had to transport the finished monolith hundreds of miles down the Nile, and you had to stand it upright at the temple without breaking it. The Egyptians pulled this off about 30 times across their entire history. The largest one they actually completed, the Lateran Obelisk now standing in Rome, weighs 455 tons. That is the benchmark for what ancient Egypt is proven to have achieved. The unfinished obelisk would have weighed nearly 3 times as much. The stone of the pregnant woman at Baalbek, the largest worked monolith in the ancient world, weighs around 1,000 tons. It was never moved. The Egyptians at Aswan were attempting something heavier than that, and they thought they could not just move it, but lift it, float it, and stand it up. The quarryman's nightmare. The first serious modern study of the Aswan quarries happened in 1922. A British Egyptologist named Reginald Engelbach spent years documenting the operations preserved in the granite. His reconstruction is still what mainstream archaeology teaches. The technique, according to Engelbach,
We'll go in the other side. I don't know if this is probably blocked off here, but look at the size of this guy on the left here.
And I've been waiting to see. Oh my god! And I was waiting to see that one.
was simple and brutal. Workers used dolerite hammer stones. Dolerite is harder than granite, to pound the surface into dust. Strike after strike, millimeter by millimeter, they pulverized trenches around the desired block. It was slow. It was effective. The evidence is everywhere in the quarry. Dolerite balls have been found at the site. Pound marks scar the rock faces. The trench shapes match what hand pounding would produce. Experimental archaeology has confirmed the method works. In 1999, a Nova episode followed stonemason Roger Hopkins and Egyptologist Mark Lehner as they tried to quarry, transport, and erect an obelisk using only ancient techniques. They quarried it with dolerite. They moved it on wooden sledges. They stood it up using a sand-filled pit. The obelisk they built weighed 25 tons. The unfinished obelisk is 50 times heavier, and this is where the official story starts to crack. The surfaces that don't match. Engineer Christopher Dunn, author of Lost Technologies of Ancient Egypt, has spent years examining the Aswan quarry up close. He is not an Egyptologist. He is a precision machinist. He spent a career making metal parts to industrial tolerances, and what he sees in that quarry contradicts the dolerite hammer story. Some of the quarry surfaces are flat, not roughly flat, flat to a degree that hand pounding with stone balls does not easily produce. Some of the corners in the extraction trenches are sharp, sharper than rounded dolerite balls would create. The efficiency implied by the scale of production exceeds what experimental archaeology has ever demonstrated. When Hopkins and Lehner ran their Nova experiment, They tracked how fast the dolerite hammer technique actually removes granite. The number was uncomfortable. Working a full shift, a single pair of hands could pulverize less than a fraction of an inch of stone surface per day. Scale that up to the unfinished obelisk's trenches, hundreds of cubic meters of granite reduced to powder around all four sides. And the labor numbers run into territory that the recorded Egyptian workforce at Aswan cannot account for. Mainstream Egyptology rejects Dunn's conclusions. They do not address his observations. The flat surfaces are explained as coincidence. The sharp corners are explained as preservation artifacts. The scale is explained by lots of workers and lots of time. But Dunn's question never goes away. If the Egyptians were really doing this with stone balls and copper, where are the millions of cubic meters of granite dust that the technique should have produced? Where are the broken hammer stones that millennia of pounding should have left behind in industrial quantities? The dust alone, if you take the official methodology at face value, would have filled the quarry to the brim. The math on the cleanup does not balance. There are also the surface details. Look closely at the trench walls around the unfinished obelisk, and you can see what Dunn is describing. Long, parallel grooves running the length of the cuts. Concave scoop marks the size of a dinner plate, evenly spaced, suggesting some kind of repeating mechanical action rather than thousands of individual hand strikes. The sides of the obelisk are smoother than the trench walls. The transitions between surfaces are crisp, where pounded surfaces would be ragged. Dunn does not claim to know what tool produced these features. He simply points out that the official tool, a stone ball swung by a tired man, does not match what is preserved in the rock, and no Egyptologist has answered him in a way that the engineering community accepts. This is what mainstream archaeology cannot afford to engage with, because once you accept that one part of the story is incomplete, you have to ask what else is incomplete. The math that does not scale. Now, imagine the crack never appeared. Imagine the Egyptians finished the job. What happens next? First, they have to separate the obelisk from the bedrock on its underside. The standard hypothesis involves wooden wedges. Slots cut into the stone, dry wood inserted, water poured in, the wood expanding and splitting the granite along a planned line. Romans did this. Medieval stonecutters did this. Whether the Egyptians did this is debated. The unfinished obelisk shows no clear wedge slots on its lower face, so that is already a guess. Assume it works anyway. Now the obelisk is loose in a granite pit. It is 137 feet long. It weighs 1,200 tons. The walls of the pit are solid stone. How do you lift it out? You cannot roll it. The shape is rectangular, not cylindrical. You cannot drag it up a slope. The friction is enormous, and the quarry geometry does not allow a gradual ramp. The mainstream answer is earthen ramps inside the pit, wooden sledges, lubricants, and human labor pulling on ropes. This has never been tested at anything close to the scale required. To drag a 1,200-ton object on wood, you have to overcome static friction that would snap any rope system the Egyptians are known to have built. You also need more workers than physically fit in the quarry. Then there is the river. The destination was Karnak, over 100 miles north. The Egyptians moved obelisks on barges. We have a relief at Hatshepsut's mortuary temple at Deir el-Bahari that shows the operation. A single barge carrying 2 obelisks, towed by a fleet that required 840 oarsmen to maneuver. The obelisks on that barge weighed 320 tons each. The unfinished obelisk would have weighed nearly 4 times as much. No barge of that capacity has ever been documented. No ancient text describes one, no depiction survives. The vessel would have to distribute 1,200 tons across its hull without breaking, float despite the load, and stay stable in river currents. The hull would need to be longer than 200 feet, with internal bracing systems that the Egyptians are not known to have developed. The rigging required to keep it from rolling under a top-heavy concentrated load would exceed anything visible in the Deir el-Bahari relief. Either the Egyptians built something they never recorded, or they had no plan for this part of the project. There is also the loading problem. To get a 1,200-ton obelisk onto a barge in the first place, you need a launch site, a stretch of riverbank, engineered to slope down into the Nile at a precise angle, with the barge floated up against it at exactly the right water level so the stone can slide aboard without capsizing the vessel. The seasonal flood cycle of the Nile gives you a narrow window each year when the water sits at the height needed for this kind of operation. Miss the window and the obelisk waits in the quarry for another 12 months. Hit the window with anything less than perfect coordination, and the barge tips, the stone slides, and a project that consumed years of labor disappears under the river forever. Then comes erection. The obelisk arrives at Karnak. It is lying flat. You have to stand it up. The known technique uses a sand-filled pit. The obelisk is dragged onto a ramp, its base extended over the pit, and workers slowly remove sand from below. As the sand drains, the base drops, the upper portion tilts up, and ropes guide it into vertical position. This works for obelisks in the 200 to 400 ton range. At 1,200 tons, the physics break. As the stone tilts, the center of gravity shifts. The forces on the base spike. At a critical point, the obelisk's own weight starts driving the rotation faster than any human team can control. For a 300-ton stone, this is manageable. For a 1,200-ton stone, it is catastrophic. The object would slam into final position, with forces that crush wooden bracing, snap rope, and shatter the pedestal. And there is a second problem nobody talks about: the pedestal itself. A finished 1,200-ton obelisk concentrates its entire mass on a base only a few meters wide. The compressive load on whatever stone block sits underneath it is staggering. The base block has to be carved with millimeter precision because any uneven contact point becomes a stress concentrator that could fracture the obelisk on its own weight. We have no record of the Egyptians ever cutting a base block to that tolerance for an obelisk of this scale, because they never had to. The math does not work, the physics doesn't scale, and the Egyptians started carving the stone anyway. If the idea that ancient Egypt was working with techniques we can't reconstruct sounds insane, wait until you see what's coming next. Hit subscribe before you forget. This gets stranger. The overreach hypothesis. The conventional answer is that they overreached. The crack saved them from a failure they would have hit later. The pharaoh wanted the biggest obelisk in history. The quarrymen did their best. When the crack appeared, everyone breathed out. This is plausible. It is also condescending. The men who ran the Aswan quarry were not amateurs. They had quarried and moved dozens of obelisks across centuries. They knew granite. They knew logistics. They knew exactly what their workforce could and could not do. To assume they simply miscalculated, that they began a project 3 times larger than anything they had ever finished, with no plan for how to complete it, is to assume a level of incompetence that the rest of the Egyptian engineering record flatly contradicts. These were the same people who built the pyramids, who aligned monuments to stellar precision, who moved 80-ton granite slabs into the burial chamber of the Great Pyramid with margins of error you can measure in millimeters. They did not start a 1,200-ton project on a hope. There is also the political reality. A pharaoh, and especially Hatshepsut, who ruled with a male regnal title and constantly had to justify her power through monumental display, could not afford a public failure of this scale. A botched obelisk is not a private disappointment. It is a humiliation visible from the temple gates. The court astronomers, the priests, the engineers, every official whose career depended on the project succeeding would have raised the alarm before a single chisel touched the granite if the plan had no path to completion. Projects of this magnitude do not start without somebody at the top signing off that the operation is achievable. Somebody signed off. We do not know what they were looking at when they did. The alternative is that they had techniques we cannot reconstruct. And this is where the field gets quiet, the comparison that should humble us. In 1586, Pope Sixtus V ordered the relocation of the Vatican obelisk. It weighed 330 tons. The move covered 250 meters and required nearly 1,000 men, dozens of horses, and 40 capstans operating in coordination. It is the most thoroughly documented large stone move in history. It worked, but it took the full sophistication of Renaissance engineering, metal hoisting equipment, calculated rope systems, military-grade discipline, and the obelisk still weighed only 330 tons. The unfinished obelisk would have weighed nearly 4 times that. In the 19th century, the so-called Cleopatra's Needles were moved from Egypt to London and New York. The London obelisk weighed 200 tons. It traveled inside a custom iron cylinder towed by a steamship. The New York obelisk, similar in size, required the United States Navy, custom marine cradles, and railroad transport across half a continent. These were 200-ton stones. They needed industrial-age technology to move, and they almost broke the budgets of empires to do it. The Egyptians, with copper tools and human muscle, intended to move something 6 times heavier than anything Cleopatra's needles ever weighed. Either they had techniques we cannot reconstruct, or they were attempting a project they could not complete. The textbooks have chosen the second option. The stone is the rebuttal, the quarry that never updated. The crack in the granite is visible to anyone who walks into the quarry today. It runs diagonally across the body of the obelisk, a long, jagged line from one face to the other, a flaw in the stone that would have made the finished monument unusable. The internal stresses of transport and erection would have shattered a cracked obelisk somewhere between the river and the temple. So, work stopped. That part of the official story is probably true, but it does not answer the bigger question. If the crack had not appeared, what would have happened next? The textbooks say the Egyptians would have used the same techniques they used for smaller obelisks, just scaled up. The textbooks assume scaling. The engineering reality is that scaling does not work that way. Forces are not linear. Materials have hard physical limits. Rope, wood, and human muscle do not multiply with ambition. Museums update their displays when new evidence breaks old assumptions. The Aswan quarry has not been updated. The explanation given to tourists today is the same one Engelbach wrote down in 1922. Dolerite hammers, wooden sledges, human labor, an unfortunate crack. The questions engineers raise are not addressed. The scaling problem is not discussed. The assumption is that the Egyptians knew exactly what they were doing, which is probably true, and that we know exactly what they were doing, which may not be. The unfinished obelisk is the largest piece of stone ever worked by human hands. 3,500 years ago, people with copper and bronze tools sat in a granite pit on the banks of the Nile and started cutting it loose. They intended to take it 100 miles north and stand it on a temple platform. They walked away when the crack appeared. Walk into the quarry today, and the scale only registers when you stand next to it. The body of the stone runs longer than a tennis court. The pink granite catches the southern sun and turns the color of dried blood in late afternoon. The surfaces are scarred with the shadows of the trenches that surrounded it. You can climb down into the gap that was cut on the north side, the channel where the workers stood pounding for years, and see the size of the body looming above your head like a wall. Tourists pose for photographs. Nobody mentions the engineering problem. The stone is still there. The pit is still there. The crack runs across the granite exactly where they left it. The explanation has not moved an inch since 1922, and the longer you stand at the edge of that quarry, the more the discomfort settles in. Because the official story is not just incomplete, it is incurious. The questions that ought to be on every tour guide's lips are missing. The scaling problem, the barge problem, the erection problem, the surface tolerance problem. None of it gets discussed at the site, none of it gets discussed in the textbooks, and none of it has been resolved in 100 years of engineering scrutiny. The crack saved them from having to try, or perhaps the crack saved us from having to explain how they succeeded. So, the question that never gets asked in the textbooks is this: were the Egyptians overreaching, or were they working with knowledge we lost? Drop your answer in the comments. And if you want more mysteries the official story can't explain, hit subscribe. The next one is already waiting.